This is section 4.2, the unit circle and trigonometric functions of real numbers. Now, if you learned trig in high school, you probably first learned it by talking about right triangles, and that's one very valid approach to trigonometry. But also, we can talk about the unit circle approach. Now, they both have very definite uses, but in calculus, it's often more appropriate for us to think about it in terms of the unit circle. So that's where we are starting first. We are going to come back to right angles in chapter 6, okay? So in this section, you're going to feel like I'm defining things twice, and that's the truth. There are, even within the unit circle approach, the trig functions can do multiple things, and the notation we use is slightly different depending on what it is we are trying to accomplish. So just be aware of that. Don't feel like I'm changing things up on you. They are very, very, very closely related, and I hope I make sure that that is completely clear to all of you. Okay? Now, before we get started on everything else, I want you to remember that the standard form of a circle, if our center is the point HK, and our radius is r, then this is our normal equation. X minus h squared plus y minus k squared is equal to the radius squared. Now, when we're talking about the unit circle in particular, unit meaning 1, our radius is defined to be 1. So if we compare this to this formula we have down here, our r is 1, 1 squared is 1. So that squared didn't disappear, it just happens that 1 squared is 1. And the unit circle is one that is centered at the origin, so h and k are 0. So this is just a special case of a general circle, okay? Now, let's talk about some properties of the unit circle. Remember that circumference is the distance all the way around a circle, and the normal circumference formula is 2 pi r. Well, our radius is 1, so the circumference in particular for our unit circle is just 2 pi. Now, what this means is the arc length, the distance all the way around the unit circle, is 2 pi units. Okay? Now, let's also talk about some symmetry. We know that if we square a negative number, we get the same answer as squaring the positive number. And since x and y are both squared, that means that we have some things that are always definitely going to be on the circle. Because if a squared and b squared we get 1, then a squared and negative b squared is also equal to 1, and so on and so forth. Now what this means for us is if we know, say this point is on the unit circle, then we know that this point is also on the unit circle, because if you square negative numbers, it's the same. Here, if one of them is negative, or here the other is negative, it's also going to be true. And since we are adding square numbers, you could theoretically switch the x and the y, and that point is also going to be on the same circle. Now, this ends up being some very important properties for us. And if you're very visual, one of the things you might want to notice is that this right here always makes a nice little rectangle, okay? And then this is where you switch in the x and the y. We're not going to be using that as much, but it is on the circle. But if you think about making these as a rectangle, it will help you use the unit circle in a little bit. Okay, so let's just look at some example problems. They ask us to determine whether the given point is on the unit circle. So what they are asking us to do is to verify that x squared plus y squared does give us 1. If it gives us any other number than 1, it is not a point on the unit circle. So let's just plug this in. For 12/13 and 5/13, this would be 12 over 13 squared plus 5 over 13 squared, and we're hoping that it equals 1. Well, if you square each of these, you get 144 over 169 plus 25 over 169. You have a common denominator, and if you add that across the top, you get 169 over 169, which does equal 1. So yes, this point is on the unit circle. Let's do the same thing for the point -3/4 and 1/4. If I square this, -3/4 squared, and I add it to 1/4 squared, does that give me 1? Squaring this gives me 9 over 16 plus 1 over 16, which gives me 10 over 16, and I don't need to reduce that just to know that it does not equal 1. So this point is not on the unit circle. Okay, now let's go into a slightly different type of problem. Here we are given a partial ordered pair, and they want us to find all the numbers, if there are any, that have this y component. Now, if we're talking about a circle and whether we have the y component or the x component, if my y values are the same, often I will hit the unit circle more than once. I mean, if I'm talking about up here and not hitting it at all, that's one thing. But often you're going to have two answers, whether your x or your y is the same. It is possible to have only one, like if you just barely touch the circle. It's possible to have none, but a lot of the time you're going to have two. So if I look right here and I want to find all the values of x that will work if my y value is -1/3, I will plug in u squared plus -1/3 squared, and that needs to equal 1. So I have u squared plus 1/9 is equal to 1. Subtract 1/9 from both sides. You have u squared is equal to 8/9. And now I use the square root property. The square root of u squared is u, and this equals plus or minus, you don't forget the plus or minus, 8/9. And then if you simplify this, this is plus or minus 2 square roots of 2 over 3. So we did get two x values that will work for that point. Now, I do want to remind you that you will be expected to simplify your radicals, and some calculators will do that for you, some will not. Also, when we're dealing with these trig functions, you're often going to be dealing with square roots, and they are almost always rationalized, meaning you do not keep the square root in the denominator. We'll be touching on that more in a bit. Now let's do the same type of problem here, except we're missing our y value. Algebraically, it ends up working the same way. I plug in my x value and square it. And then I'm going to add my y value and then set that equal to 1. So I get 16 over 9 plus u squared is equal to 1. Now if I subtract 16/9 from both sides, I get that u squared is equal to -7 over 9. Now to solve this for u, I should use the square root property and take the square root of both sides. And if all I were interested in was the algebraic answer to that, I could do that. I would have imaginary answers. But we're talking about needing a y coordinate, and we can't graph an imaginary number. So if I try to take the square root of both sides, I get imaginary answers, and so this doesn't work. There are no values for u that will place this on the unit circle.